Hey, I'm Charlie Thompson, and welcome to the pre-lab video for Lab7 Rain. Before we get started, I'd like to talk a bit about physical geography in general and how it relates to lab. So, one of the main goals of physical geography is trying to understand why a place has the characteristics it does. And things that we pay attention to, things like temperature range, average temperature, how much rainfall a place gets. Those are all elements that go into helping us understand the characteristics of a place, but this is about why that place has that characteristic. And that often has to do with its location, primarily latitude, which is responsible for 95% of everything in physical geography. If it's not latitude, it's probably something to do with plate tectonics that's creating whatever it is that we're looking at. So, big theme in physical geography is trying to understand why a place has the characteristics that it does. And as an example of this, a friend of mine was from Singapore. She grew up in Singapore, and it occurred to me, because she was going to school at UC Davis, that until she came to UC Davis, she had never experienced cold rain. And I thought about that and thought about it and thought about it. And I think, wow, that would just completely blow my mind. If I went someplace expecting it to be exactly like home and it was really different, like if I went to Singapore, the rain would be hot. It's in the tropics. It's always warm. It's a different precipitation mechanism. They have hot rain in Singapore. In Davis, in Sacramento, we get rain in the winter, and the rain is caused by a combination of a cold air mass and a warm air mass, and the cold air mass is on the ground. So we get cold rain, but that's just one tiny example. So if you know where a place is, you often know or can look up what all the characteristics of that place are, which is the exact opposite of the way information is often presented in lab. Like all of the humidity stuff we did in the last lab, Lab 6, all of the humidity stuff was trying to figure out, is it going to rain or not? And that's what this lab is about. But then it occurred to me, I could spend an entire week or two. You could learn all kinds of new problems and math skills. But in the end, all you're trying to do is calculate out, is this parcel going to rise, which might give us rain, as opposed to looking at different places on the globe and trying to figure out why it's raining there. So location is everything. If you know where a place is, you know why it's raining there. And so I think a lot of the difficulty in lab is because things are artificially hard. If you were given all the information, or if you're given more information, it would be much easier. For example, when we get to the chapter on plate tectonics, part of it's going to be looking at locations of volcanoes and trying to figure out what kind of volcano, what are the characteristics of that volcano. And in past semesters, I got comments from students saying, how am I supposed to know what kind of volcano it is just by looking at it? And that's missing the point. We weren't looking at the actual volcano, but where it is. If you know where a volcano is, if you know what kind of plate tectonic boundaries are by that volcano that are creating that volcano, you can make a whole bunch of really good guesses about the chemical composition of the magma, whether that volcano is going to explode or just ooze, and all that is a function of its location. So, I spent a week throughout the old lab, and I created this lab that I think will be much, much, much more meaningful in terms of why is it raining in different parts of the world, as opposed to just finishing up the lab doing 2 weeks of math problems that ultimately wouldn't mean anything to you. So location is everything. Tectonics lab, you'll see what I'm talking about. Rain. Let's talk about rain. So if you want to make it rain, you have to lift air up. And there's lifting mechanisms. There's 4 reasons that air lifts up. We'll talk about lapse rates, which is the rate that the atmosphere cools off. We'll talk about adiabatic rates, which are the rates that a moving parcel of air will change temperature at. I'll go through a bunch of examples. And I'll make sure that you know what the critical tasks are for this lab and where to find the answers. So, rain. If you want to make it rain, you need to lift air up. If you want to make it rain, you need liquid water in clouds. Well, if you walk out your front door, usually, unless it's foggy, you can't see liquid water in the sky. So if you want to get liquid water in clouds, you need to get the water vapor to condense. And the way we condense water vapor is by cooling air. So as air cools, the relative humidity goes up. Eventually, if you keep cooling air, it'll hit dew point temperature. Dew point temperature, that's the temperature at which water vapor will begin to condense in a given blob of air. And in order to cool air below dew point, you need to lift it up. That's pretty much the only way to cool air, is to lift it up. As the air rises, it expands and cools. That's it. Rising air expands and cools. Rising air expands and cools. Sometimes I overemphasize things. I'd like to apologize. I get excited. But, seeing things more than once is always good. Review is excellent. So, as the air cools below the dew point temperature, water vapor will condense. So, to make it rain, you need to lift air up. There are, as I mentioned, 4 lifting mechanisms: convergent, orographic, frontal, and convective. And there are places that are associated with these types of lifting mechanisms. And there are characteristics of these lifting mechanisms that we can look at in earth.nullschool.net and figure out, oh, this is convergent or orographic or whatever it is. So let's start with convergent lifting. Convergent lifting is air flowing into an area of low pressure. As you know from previous chapters, hopefully the crash course geography video where Alize is talking about low pressure is associated with rising air and rain. So all along the ITCZ, you've got air sinking, making the subtropical highs. You've got air sinking, making the subtropical highs, and then it rushes or flows back to the ITCZ and then rises. So all across the equator, following the subsolar point, there's the ITCZ where you've got the northeast trades and the southeast trades. Ooh, this is a good diagram. You'll probably want to come back to this later. This is actually a screenshot from earth.nullschool.net. It's an excellent example of the way it looks along the ITCZ with the northeast trades and the southeast trades coming together. This is probably the 3-hour precipitation accumulation layer. I'll talk more about what some of the layers are in earth.nullschool.net that you can use for these problems. But looking at this, you've got the northeast trades, you've got the southeast trades coming together at the ITCZ, lifting air up, making rain, and that's an example of convergent lifting. So air flowing into an area of low pressure is convergent lifting. When air runs into a mountain, it gets lifted up, expands, you get rain. If you run out of mountains, the air stops getting lifted, the rain stops. If the air sinks, it heats up and dries out, and then you get what's called a rain shadow. On the downwind or leeward side, the windward, the side facing the wind, is wet. That's where we find forests. On the rain shadow side, that's where we find deserts. So I mentioned the air runs into the mountains, it gets lifted up, it expands and cools, you get rain, and then when it sinks, it gets heated by compression at the dry adiabatic rate, and you end up with a rain shadow. Frontal lifting is when 2 different air masses collide, a cold air mass and a warm air mass, and always the warm air mass is going to get lifted up. So with frontal lifting, we'll be looking for a linear feature, that is to say line-shaped, where these 2 blobs of air are meeting and the warm air is going up. Warm air mass, cold air mass, the warm air always goes up because warm air is less dense. Convective lifting, I think, is the simplest, easiest to understand. Sun shines in the ground gets warm, the warm ground warms the air touching the ground, that air gets warmer than the air around it, and it rises and makes little puffy clouds. So convective lifting is the feature that's most associated with atmospheric stability, which is an incredibly complicated idea that we're not really going to spend a lot of time doing the math on. We're just going to look at the CAPE index, which is a number that indicates how much energy there is to make thunderstorms. Anything over 1,000 rather, CAPE over 1,000, you can have thunderstorms. So that also is going to be pretty simple. You're just looking for areas when you're trying to find areas of convective lifting, you're going to be looking for areas that have CAPE values higher than 1,000. Convergent, air comes together, for example, along the ITCZ, other places as well. Hurricanes, probably an example of convergence. Orographic, air runs into a mountain and goes up. It is the most consistent, I'll keep saying that. Orographic is the most consistent. The highest rainfall values in the world are associated with orographic lifting because it doesn't matter if the blob of air is warmer than the air around it or not. It's rising because there's a mountain there and the wind is blowing into the mountain, so the air goes up. Frontal is when you have warm air masses and cold air masses colliding, the warm air goes up. And convective, sun shines on ground, ground gets warm, warm air rises. It depends on atmospheric stability. So it's really convenient that earth.nullschool.net has a layer of data that will show us places that have unstable conditions, and that's where we would expect to find convective lifting. So let's go into these a little bit more. Processes that lift air. If you want to make it rain, you need to lift air up. There's convergent. Orographic, air is lifted up by a barrier like a mountain. Frontal, warm air runs into cold air, gets lifted up. And convectional, local surface heating causes warm air to rise. So, for example, convergent along the ITCZ, you've got the northeast trades, you've got the southeast trades coming together at the equator. You've got warm, moist air rising, expanding, cooling, making thunderstorms, for example, every day as a result of convergent lifting. Convergent lifting. Air flows into an area of low pressure at the surface and rises. So we're going to be looking for low pressure. So, for example, let's see if we can't get the northeast trades going. There you go. Northeast trades, southeast trades coming together, and the only place the air can go is up. And so we've got this belt of clouds that follows the subsolar point, north and south with the seasons. Orographic lifting, the air rises and cools, and then once you run out of mountains, the air sinks and gets compressed, making Chinook winds. In the Pacific Northwest, these dry, hot winds are called Chinook winds. Orographic lifting in Washington state. Here's Mount Rainier. They're getting 126 inches of rain on the windward side, and on the leeward rain shadow side over here in Yakima, there's a picture of what it looks like over at Yakima. They're getting about 8 inches. 126 inches. This is a temperate rainforest. 8 inches. That's probably a desert because of the rain shadow effect. Mount Waialeale is the wettest place in the world. They get an average of 486 inches of rain. Here is the caldera from the volcano on the island of Kauai. And the trade winds actually funnel right into this caldera, get lifted up, and you get 486 inches of rain on the windward side. On the dry side, they get about 20 inches. 486, 40 and a half feet of rain, 20 inches of rain on the dry side. Let's look at some more pictures. This is the summit of Mount Waialeale. That is the weather station at the summit of Mount Waialeale, the wettest consistent place in the world. Here we have the road to Waialeale showing the ferns and the sort of lush vegetation you'd expect to find at a place that's getting 40 feet of rain. And then the dry side on the island of Kauai getting 20 inches of rain a year. In California, we see the same thing. This is a map of rainfall in millimeters. So 1,000 millimeters are about 3 feet. So the dark blue, it's about 6 feet of rain. And you can see there's two patterns in California. There's latitude, subtropical high, polar front, and elevation. This is an elevation map. High elevation, lots of rain. Low elevation, little rain. Dry side, so here we've got the crest of the Sierra. In fact, there's two rain shadows, right? So as storms come in, they're going to hit the Coast Range and rain, and then you've got the rain shadow of the valley, and then the Sierra Nevada, and then a second rain shadow into Nevada. Same thing with these interior deserts. There's less rain in general, but then whatever rain there is hits the Coast Ranges or the Sierras or the Transverse Range, so there's not a whole lot of rain left by the time you get to the east side of the Sierras over into Nevada. And it's interesting to think that 30 million years ago, the Sierra Nevadas hadn't been lifted up. Nevada would have been much wetter. because the Sierras were not stealing their rain. The rain just wouldn't have fallen here. It would have kept, the clouds would have kept going, so there'd be more even rain across California and Nevada before the uplift of the Sierras. So with orographic lifting, the most important thing is, hi, I've made this map. I've put links. This is the elevation diagram or elevation map that you're going to use for this lab. They're color coded. Everything under 1,000 feet is this dark purple. And then 1,000 to 2,000 is this lighter purple. So just to make it easy for this lab, if the elevation is 1,000 feet or less, it's not orographic lifting. Just want to make that super easy so you're not stressing out about, well, it's getting lifted a little bit. No, don't even worry about it. The whole West Coast is lined with mountain ranges. We've got the Andes, the Mexican Cordillera, we've got the Sierra Nevada, and then we've got the Cascades going up here because there's a convergent tectonic boundary running down the west coast of North and South America. And so it occurred to me that the westerlies, the prevailing winds in the mid-latitudes, are bringing storms across the ocean, and then they run into mountains. Same thing's happening down here in the southern hemisphere. In the mid-latitudes, the westerlies are the prevailing wind. And it's interesting, the driest place in the world is right here. And you're thinking, well, it's really high, except the wind is coming from the other side. So the rain shadow is actually on the coastal side of this mountain range down in South America. Same thing with Mexico. It's like the equivalent desert area of Mexico is down here in the Atacama. There's a weather station that went 14 years in a row without recording any rain, and 1/100th of an inch counts as measurable rain. Tibetan Plateau, Ethiopian Highlands, the spine of the mountains in Papua New Guinea and Indonesia. Those are all examples of places that are higher and therefore wetter. But for this lab, for orographic, this is the diagram you're going to use, and just take a look. And if it's raining and the wind is coming from the ocean blowing into the mountains and it's raining and the mountains are higher than 1,000 feet, that's orographic. You're done with that question. Move on to the next one. I'll say that again, though. To determine if it's orographic, you're going to look to see if the wind is blowing from the ocean to the land. And then, is it raining in the land in a place where the elevation is higher than 1,000 feet? And if it is, that's orographic. All right, frontal lifting. Warm fronts, warm air mass moves into a cold air mass. The warm air moves up and over the cold air. Warm fronts on the ground are about 600 miles wide. They move about 15 miles an hour. So here we've got a side view of a warm front. So from the actual contact point between the two air masses, like this is the warm air mass and here's the cold air mass. The warm air mass is moving up and over the cold air mass. And from the time you'd see the first cirrus clouds till rain, it's about 600 miles wide. The whole system would be moving this way about 15 miles an hour. The warm air is less dense, so it doesn't have a lot of mass, and it kind of slowly pushes the cold air out of the way, as opposed to a cold front, where a cold air mass moves under a warm air mass. The cold air lifts the warm air. Cold fronts are about 250 miles wide. They're much more narrow. They move faster. They travel about 25 miles an hour. So you'd expect to see heavier rain for a brief amount of time from a cold front. And here we've got a picture of a cold front. Cold air is moving along the ground. This one I think is really easy to understand. In fact, that's why I put that video of a roll cloud in the information for this lab. It's just like the cold air moving along the ground, shoving the warm air up. So you get heavy rain briefly because the cold air is very dense and pushes the cold air out of the way pretty easily. Oh, yeah. One other point I want to make, and I'll make it a couple other times. One of the keys to finding fronts is looking at the different directions of the air. So here, the cold air is moving along behind this, behind the warm air. The cold air is moving along the ground, lifting up the warm air. But the cold air is coming perpendicular to this line on the ground that we call the front, which is the line of contact between the cold air and the warm air. And in front, the air is going to be blowing. I wouldn't have drawn them like that. I would have drawn them more parallel to this line. So behind, the motion of the cold air is coming in perpendicular to the front, and in front of the front, the air is blowing parallel to this line. We'll take a look in earth.nullschool.net. You'll see what I'm talking about. Frontal lifting. Let's look at an animation. Let's look at a cold front. I mean, not much to see. We've got cold air moving along the ground, pushing the warm air up. So you get heavy rain, often thunderstorms, very briefly though, and then behind it you get cold air. And this is the way the storms are when they blow through and they finish. It's usually cold and clear because this cold, dry air is actually what's moving the warm air up. So warm front, exact opposite. You've got warm air slowly moving up and over and pushing the cold air out of the way. That's good enough. They often travel together with a warm front in front and a cold front behind. They form these things called mid-latitude cyclones. So frontal, the other clue for frontal is it's in the mid-latitudes. So I've tried to really simplify it and come up with obvious examples for the questions. I know it's all brand new for you. So the two things we're looking for with mid-latitude cyclones are they in the mid-latitudes? And is the wind coming behind the front blowing perpendicular and the wind in front of the front blowing parallel? So here you can see like the front would be right in here. You can see this dry cold air coming in behind, lifting up the warm air. Very nice. Oh yeah. All right. Mid-latitude cyclones, warm and cold fronts found together, spiraling around a center of lower pressure. The fronts are caused by the conflict between the warm maritime tropical and the cold continental polar air masses. So here's what I'm talking about. This is a cold front. This is a warm front. So the warm air is coming in perpendicular to the warm front, but in front of the warm front, there'd be cold air blowing, coming into this area of low pressure, rotating counterclockwise. So the air here would be going parallel to the front. This warm air that's coming up, that's coming perpendicular to the warm front, this warm air is blowing parallel to the cold front, and the air behind the cold front is coming in perpendicular to this front. So that's what we're really going to be. Linear features, lines of clouds, and an abrupt shift in wind direction, a 90-degree shift. So this wind is coming out of the south. This is coming out of the west. This is coming out of the south. The air up here, the wind would be coming from the east if we had that arrow. Here is a cold front. Here is a warm front. This warm air is coming up and moving on top of this cold air. This cold air is spiraling over here, and then there'd be a center of low pressure, and so you'd get the colder cold air moving along here, running into this warm air, lifting up the warm air, making a cold front. So the cold air pushing along, moving along the ground, lifts up the warm air to make a cold front, and in front of the cold front, the warm air is moving north, running into this cold air, getting lifted up and making a big wide warm front. And I wanted to get to the end. There's a cold front. There's a warm front. Now we've got occlusion. Typically, this process takes several days. So you've got the cold air moving along. You've got the warm air getting shoved up over the cold air. The cold air lifts up the warm air, making a front. Mid-latitude cyclones are the names for these. Let's take a look at some examples. Okay, so here we've got a front, and we've got warm air coming up here. We've got cold air coming along here. This line right in here would be the front. So this is what I'm talking about with a 90-degree shift, that this wind is coming out of the southwest. This wind is coming out of the west. That's a good example of a front. Along this line, we would have convergence. We've got the southeast trades and the northeast trades. This would also be convergence. This is a little tropical storm of some sort. In fact, if we turn on the sea level, I might as well talk about these things now. So the default view if you just go to the website, is the wind layer. There's also a layer of temperature. It's showing surface temperatures. The 3 HPA is the 3-hour precipitation, which is rain accumulation. It's how much rain is going to be falling. That's the layer that you'll use to see where it's actually raining. So here along the ITCZ, we've got rain. Here we've got this cold front making rain. Can't really see the warm front over there. Looks like there's also some sort of frontal structure over here. That's too confusing. I wouldn't ask you about that. But you can see the ITCZ. You can see this front and the difference in the direction of the wind, 90-degree wind shift from one side of the front to the other side of the front. Really one of the big things that we're going to be looking for. Let's take a look at another one. Okay, so now we've got a couple fronts. We've got a center of low pressure. We've got cold air coming down here. We've got warm air coming up here. And there's a 90-degree difference between the direction of wind coming out of the southwest, coming out of the northwest. Same thing over here. Warm air coming out of the southwest, cold air coming out of the northwest with the ITCZ. Continuing on with the layers, we've got the 3-hour precipitation showing us where it's raining. And CAPE. CAPE is convective available potential energy. Anything over 1,000, like right here, it's 3,000. Big thunderstorms. Over here, 1,900. So double the value required. In fact, at the Amazon, 1,300 joules per kilogram. Those are some pretty big values. There's also the total cloud water. You can turn that on to see what the clouds look like. Often there's clouds along the ITCZ. Here's these fronts. There's the big, broad, wide, warm front. There's the narrow, cold front. TPW is total precipitable water. That's the amount of all the water in the atmosphere that could fall as rain. You can see the ITCZ, always massive values along the ITCZ. So, yeah, you can see that. Very nice. There's a front. There's a front. And I was going to say, if I turn on the CAPE, yeah, high values. So for the convective rainfall, you're going to go for the high CAPE values. For frontal, you're going to look for shifts in the wind. For convergent, you're going to use sea level air pressure. That's one of the things you could look at, like this belt along here. That'd be convergence along the ITCZ. There's air rising over here, air rising here as well. Let's take a look at another one. So now we've got total precipitable water turned on again. I wanted to open up CAPE. Oh, yeah. On this day, there would have been massive thunderstorms up and down Tornado Alley in this region. So that takes care of, let's turn on the 3 HPA. Orographic. So here we've got wind coming from the ocean onto the land. That's a great example of orographic. So now we've got examples of orographic. We've got examples of convective lifting, orographic. We've got convective lifting. We have convergent lifting along the ITCZ. And the reason we know it's convergent, we can turn on the mean sea level air pressure, and you can track, well, we've also got the wind turned on. So you've got the trade winds coming from the south, the trade winds coming from the north. If we turn on the rain, you can see that it's creating this band of rain right where these two different systems of air are colliding. So we've got convergent, convective, frontal, and orographic. I think we've now seen examples of orographic, convergent, convective, and frontal. So if I turn on the cloud water or the wind might be good. Yeah, so there's some frontal activity. That's a front. Yeah, like I said, I'll try to make these really obvious. I thought about playing around with an assignment asking you about Hawaii, but the island is so small that you really can't pick out the details. But on this day, it sure seems like they would be getting lots and lots of rain because of the direction of wind. In fact, there's the island of Kauai and the trade winds. So you've got warm, moist air running into Mount Waialeale all the time. The air gets forced up by the mountains, so they have the rainiest place in the world right there. Okay, let's keep going. So again, convectional, sun shines on ground, ground gets warm, air rises. Convection over Florida, so we'd be looking for high CAPE values over Florida. And on this example, you'd find really high CAPE values here, very low CAPE values here. So that's convective with high CAPE values. Atmospheric stability determines if it's going to rain for thunderstorms, for convective lifting. And it's the idea that an air parcel, if it's the same temperature or a different temperature, behaves differently. So the idea of stability, just the concept of stability, it's the tendency of an air parcel to either rise, remain in place, or fall. Really, all we care about is rising. If it rises, you're going to get rain. Otherwise, you don't. An air parcel that's warmer than the air around it is unstable and rises like a hot air balloon. An air parcel that's colder or the same temperature will sink or stay where it's at. It's stable. You don't get rain. We don't care. Hot air balloons are a great example of this. The hot air balloon, it's not that hot air rises, it's that hot air is less dense and therefore it rises. So if the parcel is warmer than the air around it, it's the air in the parcel is less dense and so it rises, just like oil floats on top of water. Okay, rates of cooling and warming. There are, I don't know how to divide this up. We've got the unmoving atmosphere, and we're going to call those lapse rates. There's two of them. The normal lapse rate is the average rate of cooling. If you sent a balloon up with a thermometer and you kept track of the temperature every 1,000 feet, you'd find that in the troposphere, the average rate of cooling is 3.5 degrees for every 1,000 feet you get away from the ground. So in the troposphere, which is the lower layer of the atmosphere, it's heated by the sun shining on the ground for the most part. And so as you get away from the ground, it gets colder at, on average, 3.5 Fahrenheit degrees per 1,000 feet. The environmental lapse rate, or ELR, is the actual rate. That always would have to be given to you. They send weather balloons up to find out what the environmental lapse rate is. You'll never have to figure that out. It would always be given. So unmoving atmosphere, we're using the lapse rates. There's the normal and environmental. If you're talking about a moving parcel of air, something entirely different is going on, because as the parcel rises, it expands and cools. A rising parcel of air will expand and cool by 5.5 Fahrenheit degrees for every 1,000 feet it goes up, until you get condensation. Once water vapor starts to condense, you hit 100% relative humidity, then you cool more slowly at the moist rate, 3.3 Fahrenheit degrees per 1,000 feet. Moving parcels of air, they cool or heat at adiabatic rates. The word adiabatic means a change in temperature without a loss or gain of heat. So it's kind of confusing because it seems like as the parcel is rising, the air around it is colder, so it seems like the parcel should be cooling, but that's not why a rising parcel cools. A rising parcel cools because it's expanding. That's it. A sinking parcel gets compressed and heats up. It's not because the air around it's warmer, it's because it's actually getting compressed and that's why it's heating. Rising air cools through expansion, sinking air warms through compression. Rising air expands and cools. It's 10 Celsius degrees per kilometer, 5.5 Fahrenheit degrees per 1,000 feet. So you go up, gets cooler, goes up, it expands, gets bigger, cools, goes up, expands, gets cooler. If it sinks, though, it's going to get compressed and heated, compressed and heated, compressed and heated. That's also why we get the rain shadow effect. It's this sinking and compressing and heating. Rising air expands and cools by 5.5 Fahrenheit degrees for every 1,000 feet it goes up. That's the dry adiabatic rate. Rising air cools 5.5. Sinking air heats by 5.5 degrees because the air gets compressed. When a parcel cools to dew point, water vapor condenses and releases an enormous amount of heat, 540 calories per gram of water vapor. So, once it cools to dew point, you've got a parcel that's cooling by expansion, but it's heating because of the condensation of water vapor. So you've got cooling and heating. The moist rate, 3.3 degrees per 1,000 feet. It's because you've got 5.5 degrees of cooling from expansion, but as the water vapor condenses, you've got 2.2 degrees of heating. So 5.5 minus 2.2, 3.3 degrees of cooling is the moist adiabatic rate. The lifting condensation level is the altitude at which condensation begins to occur. So when the parcel cools to dew point temperature, that altitude is the lifting condensation level. And I'll talk about how to calculate what the lifting condensation level is for a parcel. This is a picture that a former student who is now teaching geography, former student of mine, she's now teaching geography. She took this picture because she was stoked that you could see the flat bottoms of clouds indicating where the lifting condensation level was. So you've got these little cumulus clouds. This would be an example of convective lifting. The sun shines on the ground, the air rises, expands, cools, and because the air is well mixed, it hits the temperature at about the same altitude for all the different little cloud parcels. And that's why clouds are flat on the bottom. So the things that you should be able to do, and from the last chapter, last lab rather, we finding specific humidity, dew point temperature, relative humidity. We've done that. And this lab will try to figure out what the lifting condensation level is. We're not going to cool the atmosphere at the environmental lapse rate. We're going to either cool a parcel by the dry rate or the moist rate. We're going to heat parcels by the dry rate if they sink. Things that you should be able to do by the time you're done watching this video. If I tell you the characteristics of an air mass, you should be able to figure out the specific humidity, the relative humidity, the dew point temperature, and the lifting condensation level for that air mass. You should know when to use the dry rate until the parcel cools to dew point temperature, and when to use the moist rate after the parcel cools to dew point. And calculate temperature changes, 5.5, 3.3. Those are all on the cheat sheet. The cheat sheet. So, yeah, let's take a look. So let's take a look at the cheat sheet. So I made a cheat sheet. I made this table. I thought it would relieve some stress and anxiety if you had clear-cut instructions on if we're looking for convergent lifting. Where is it? Well, along the equator if the lifting is along the ITCZ. And what are we looking for? Low pressure. So if you've got low pressure along the equator with rain, it's convergent lifting. How about orographic? Well, latitude. Any. What we're looking for? Mountains. We're looking for wind blowing air from the ocean into the mountains and then getting lifted up. So look for the mountains on the elevation figure and then use the wind and the 3-hour precipitation accumulation layer to determine, are there mountains there? Yeah. Is it raining because wind is blowing into the mountains? Yeah, it's orographic. Frontal, we're going to look for those distinctive linear shapes in the mid-latitudes. Fronts make mid-latitude cyclones, so the only frontal features that you're going to find are going to be in the mid-latitudes. And the big thing we're looking at is wind direction shifting 90 degrees from one side of the front to the other. Finally, convectional, any latitude, but what we're looking for is high CAPE values. In general, CAPE values over 1,000 joules per kilogram. That's what we're looking for. So if there's low pressure and you're along the equator, it's the ITCZ and you've got convergent lifting. If there's mountains and the wind is driving air over the ocean and then up mountains, that's orographic. If you've got a 90-degree wind direction shift in the mid-latitudes, it's frontal. And then if you have high CAPE values, it's going to be convectional. I mean, in reality, like the rain that we get is a combination of frontal and orographic, depending on where you live. So nature is incredibly complex. I just tried to find really simple examples for you so it wouldn't be incredibly difficult. The cheat sheet goes over rates of cooling. Which rate do I use? I don't know. Well, if we're talking about a parcel, it cools at the dry rate until it cools to dew point. Then you're going to cool it at the moist rate. If it's the atmosphere, then you'll use the ELR. Some other stuff about lifting condensation level, some other stuff about stability, rounding numbers, a recap, and then the formulas from Lab 6, how to find maximum specific humidity. Look at the temp on the max chart. On the chart, it's all about the chart. Yeah, maximum specific humidity, dew point temperature. If you know what the specific humidity is or the temperature, you just look it up on the chart. You don't have to do any actual work. Okay, let's get back to the video. Okay, and again, some of the super important bits of information: convergent, orographic, frontal, convection, and then what it is that I'm telling you should be looking for. Low pressure, mountains, high cape values, wind direction shifts 90 degrees. All those things are distinctive. Low pressure, convergent, mountains, orographic. 90-degree shift in the wind direction from one side to the other, that's a front. And high cape values, you're going to have convectional activity. That's the main stuff. Let's go over a few other ideas, big ideas. Yeah, atmosphere cools at the environmental lapse rate. Parcels cool at the dry rate until they cool to dew point. Then it cools at the moist rate. To find the dew point temperature, you find the specific humidity, then look it up on the max specific humidity chart. It's back to the chart. The two rates, we've got the lapse rate for the atmosphere and the adiabatic rates for moving parcels. You just have to ask yourself, who's moving? Am I trying to find what the temperature is for the atmosphere? Then we use the environmental lapse rate. Are we trying to find the temperature of a moving parcel? If it's a moving parcel, then it's one of the adiabatic rates. Going up through the atmosphere cools at the environmental lapse rate. The environmental lapse rate will always be given to you. Going up through the atmosphere cools at the environmental lapse rate. If the environmental lapse rate is 5 degrees per 1,000 feet, that means the atmosphere gets 5 degrees colder every time you go up 1,000 feet. So if I give you the temperature at the surface and then ask you what the temperature is 5,000 feet above that, I'd have to give you the ELR. It's 5,000 feet. 5 times 5 is 25 degrees colder. A rising parcel cools at the dry rate until it cools to dew point temperature, rises to the lifting condensation level. After that time, it cools at the moist rate. The lifting condensation level. So now I'm going to get into the lifting condensation level. That's the level at which a given parcel of air will cool down to 100% relative humidity. To find the lifting condensation level, you need to figure out the current temp and the dew point, and then find the difference between them. So how many degrees do you need to cool? So you find how many degrees you need to cool to bring the parcel down to dew point. Then just divide that by 5.5, and that tells you how many 1,000 feet of lifting. So let's do an example. Lifting condensation level. The dry adiabatic rate's 5.5 per 1,000 feet, which is also 0.55 per 100 feet. I don't know why I'm telling you that. Might be useful. I don't know, maybe. So starting temp minus dew point divided by 5.5, that tells you how many thousands of feet above the ground is the lifting condensation level. So if you needed to cool by 20 degrees, 20 divided by 5.5 is 3.636. Yeah, so this is an important point that I'm about to make, is the answer you get, temperature minus dew point divided by 5.5, it gives you the answer in thousands of feet. So it gave me 3.636. That's 3.636 thousand feet, which is 3,600, because we're just rounding to 100 feet for this class. Let me say that again, though. 20 divided by 5.5 is 3.636, and that's how many thousands of feet you've got to lift it before you'll cool it to dew point temperature. So 3.636 thousand feet is 3,600 feet, rounded to the nearest 100 feet. Example 1, given an air mass at 77 Fahrenheit with a specific humidity of 12.5 grams of water vapor per kilogram, and the temperature of the parcel is the same as the atmosphere when the parcel's on the ground. Everything's the same temperature. It's all well mixed. So what's the relative humidity? What's the dew point temperature? What's the lifting condensation level? What's the temperature of the air mass at 5,000 feet? Let's go through these. So, given air mass at 77 degrees with a specific humidity of 12.5, first question, what's the relative humidity? Next, what's the dew point? lifting condensation? What's the temp at the air mass at 5,000 feet? And what's the new specific humidity? Because remember, we're going to find what the dew point temperature is, and then as it cools below dew point, you're going to lose water vapor until it gets as cold as it's going to get. And then we're going to use that new cold temperature to find the specific humidity of the parcel after it's been lifted up. So after the parcel is lifted and cooled, we'll find a new specific humidity. So starting number one, what's the relative humidity? Well, we know the specific is 12.5, the temperature is 77, so the max specific humidity off the chart is 20 grams. We have 12.5, the max is 20, 12.5 divided by 20 times 100 is 63%. What's the dew point temperature? Okay, so specific humidity is 12.5 grams, which falls in between 64.4 and 62.6. So we're going to always use the colder temperature. You won't get condensation. If you've got 12.5 grams, you're not going to get condensation as it cools to 64.4. You're not going to get condensation until it cools to 62.6 degrees. So the dew point temperature is 62.6 because it's the colder. If you're in between, we're going to use the colder temperature for the dew point temperature. What's the lifting condensation level? Well, temperature on the ground is 77 degrees. The dew point is 62.6 degrees. So the parcel has to cool by 14.4 degrees. There's a difference of 14.4 degrees from 77 and 62. Remember, the dry rate is 5.5, so we take the degrees it has to cool, 14.4, divide that by 5.5, and that gets us 2.6. The answer is in thousands of feet. So 2.6 thousand feet is 2,600 feet. So the lifting condensation level for this example would be 2,600 feet above the starting elevation, which was sea level. What's the temperature of the air mass at 5,000 feet? Okay, so the parcel of air cooled to dew point temperature at 2,600 feet. We already found the dew point temperature and the lifting condensation level. So the parcel cooled to the dew point temperature of 62.6 degrees at an elevation of 2,600 feet. But we're going to 5. I mean, it ran into a mountain. It doesn't have any choice. The top of the mountain's at 5,000 feet. So we've got the parcel cools to 100%. Yeah. Cools at the dry rate until it cools to 62.6. So now it's going to cool at the moist rate. From 2,600 to 5,000 feet is 2,400 feet. So it's going to get lifted another 2.4 thousand feet. And it's going to cool at the moist adiabatic rate of 3.3 degrees. So the moist adiabatic rate, 3.3 degrees of cooling for every 1,000 feet we go up. 2.4 thousand feet times 3.3 degrees is 7.9 degrees cooler. So the way I would do this is put the thousands, I would take, because this is actually in feet, I would put it in thousands. So I would move the decimal over, and 2.4 thousand, right? 2,400 feet is 2.4 thousand feet. So 2.4 times 3.3 is 7.9. I think if you forget to put your elevations into thousands or treat them as thousands, you're going to end up with, what would that be, 7,900 degrees? So yeah, if you answer, you get it 7,000 degrees, you've got to divide it by 1,000 because you forgot to convert your feet into thousands of feet. The rate of cooling is 3.3 degrees per 1,000 feet. So this is 2.4 thousand feet times 3.3, 7.9 degrees cooler. What's the temp of the air mass? Well, it's going to cool 7.9. It hit 62.6. That's the dew point. It hit that at 2,600 feet. It's going to cool another 7.9 degrees. So the temperature of the parcel at 5,000 feet would be 54.7 degrees Fahrenheit. Temperature of the air mass at 5,000 feet, 54.7 degrees. Okay, so what's the specific humidity of the air mass at 5,000 feet? We figured out its dew point temperature based on the old specific humidity, but as it keeps cooling, it's going to lose water vapor as it condenses, right? So the temperature of the air mass at 5,000 feet is 54.7, which is in between these two numbers. So we're going to pick the colder temp and take the maximum specific humidity of 8.8 grams. It's in between. We're going to take the cooler one. So now we know with a temperature of 54.7 degrees, the specific humidity is 8.8 grams per kilogram. Okay, example number 2, rising and sinking. So in this, we're going to take an air mass with a temperature of 57.2 degrees Fahrenheit with a specific humidity of 5 grams of water vapor per kilogram. We're going to lift it up to 7,000 feet, summit of the Sierras, and then we're going to drop it down to duplicate what happens after air masses move up and over the Sierra. They drop down into Reno, they drop down into Death Valley, they sink and they heat up and they get dry and they make deserts on the east side of the Sierras. So we're going to take it up to 7,000 feet, dry it out, and then drop it and heat it and see what its temperature, specific, and relative humidity are after it sinks down to 1,500 feet. So given an air mass at 57.2 degrees Fahrenheit with a specific humidity of 5 grams per kilogram, we're assuming it's at sea level. What's the relative humidity, dew point temperature, lifting condensation level, temperature of the air mass at 7,000 feet? So what's the relative humidity? We have a specific humidity of 5 grams per kilogram that's given to you. We look it up on the chart. The max at that temperature is 10 grams. Specific divided by max specific times 100 gives you the relative humidity, in this case 50%. So what's the dew point temperature? If the specific humidity is 5 grams, then the dew point temperature is 37.4. So we've got 5 grams. We're going to take the cooler temperature of 37.4. You just look it up on the chart. Now I want to find the lifting condensation level. We know the temperature, 57.2, the dew point, 37.4. So temp minus dew point divided by 5.5 tells us how many thousand feet of lifting we have to do to cool it to the dew point temperature. 57.2 minus 37.4 gives us the difference in temperatures. Divide that by 5.5, we get 3.6, which is the answer in thousands of feet. So the lifting condensation level is 3,600 feet. 3.6 thousand is 3,600. Okay, so now we know the elevation at which the parcel is going to start cooling at the moisture rate. We know its temperature. We know what the dew point is, 37.4. We know the altitude or elevation at which that'll happen. Altitude. What's the temp at 7,000? So it rises and cools at the dry rate until it cools to the lifting condensation level, or until it reaches the lifting condensation and cools to dew point. So the lifting condensation, 3,600 feet. So we know that the air mass is 37.4 degrees at 3,600 feet, but we're going up to 7,000 feet. So 37.4, we have 3,400 feet more lifting. That's 3.4 thousand feet. So 3.4 times 3.3 is 11.2 Fahrenheit degrees cooler. So the temperature of the parcel at 7,000 feet is going to be 37.4 minus 11.2 is 26.2 degrees Fahrenheit. Now we've got the air mass at 7,000 feet. It's 26.2 degrees with a specific humidity of 5.5. How many grams condensed? It says will condense, but I meant how many grams did condense. So if the air mass is 26.2, the maximum specific humidity is 3.0 grams. We had 5. We started with 5. We know that the max at 26.2 is 3, and that's what it has, because as it cools, it's going to have the max. So it lost 2 grams of water vapor. We know what we started with. We know what the ending temperature is, and off of the ending temperature, we can look it up from the chart to find what the max is. 5 minus 3, it lost 2 grams of water vapor. Okay, so at 7,000 feet, we've got an air mass at 26.2 degrees Fahrenheit with a specific humidity of 3 grams per kilogram. what's the temperature, specific humidity, and relative humidity of the parcel if it sinks down to 1,500 feet. When the air mass sinks, it heats up at the dry rate. When the air mass sinks, it does not gain any moisture. So we're at 7,000 feet with our air mass. We're going to sink down. As it sinks from 7,000 feet to 1,500 feet, that's going to be a decrease of 5,500 feet. So it's sinking 5.5 thousand feet, and it's warming at the dry rate of 5.5 degrees. So that parcel is going to get warmer by 30.3 degrees. So 26.2 plus 30.3 is 56.5 degrees. So the temperature of that parcel after it's sunk down to 1,500 feet is now going to be 56.5 degrees. And what do we want to find now? We want to find the relative humidity. So the max specific humidity is 9.4 from the chart. The temperatures in between, we're going to take the colder temperature. We've got a specific humidity of max of 9.4. So to figure out the relative, we know that we have a specific humidity of 3.0 grams. 3.0 divided by 9.4 is 0.319. So the relative humidity for our parcel now is 32%. And that's it for example 2. As a review, I put these in for the lecture slides. I didn't want to go over them now, but I thought I would run through the definition and how they're expressed and some of the information about relative humidity, maximum specific humidity, the dry adiabatic rate, the dry adiabatic rate, the moist adiabatic rate, the environmental lapse rate, the dew point temperature, lifting condensation level, how to find the lifting condensation level, and that's it. I wish you good luck on this lab, a Lab 7 on rain.